So today we're going to talk about rationalizing denominators of radical expressions. So we know that domain errors can occur. Sometimes we take square root of a negative and we see domain error. We have learned that we can use imaginary numbers for that, but if we're not using imaginary numbers, we're just staying within real numbers, then we get an error when we have a negative. So because this error can possibly happen, we say, all right, because we can get an error in a radical, and if there's a radical in the denominator, there's a problem, then let's just get rid of all radicals in denominators. All right? We don't want to have any of those radicals in our denominators. It's going to cause a problem. So how do we do this? Well, it's something called rationalizing the denominator. So that's what we're going to learn how to do in this video. So here we have example 1. We can see a fraction, and we do notice that we have our radical in the denominator, which is a problem. We want to get rid of it, but this problem kind of fixes itself. If we go to simplify our radicals, we notice that 9 is a perfect root. What's the square root of 9? It's just 3. So really all we have to do is worry about simplifying our 8, which I know is 4 and 2. And 2 and 2, which means I can take a 2 out, leave a 2 in. That is my simplified answer, and I didn't really have to rationalize. So here, no rationalizing. No rationalizing, because the perfect root kind of fixed itself. So that's something we need to be thinking. Sometimes we get wrapped up in all this rationalizing and we forget to look for the perfect roots, which is going to be a lot easier than actually rationalizing. So that actually is our first key point, is simplify perfect roots. So if you see a perfect root, you want to simplify that first. Looking at example 2, I can't simplify the square root of 5. It's not perfect, but I do know that having the square root in the denominator, the bottom of my fraction, is going to be a problem. So I need to figure out how to get rid of that. So here we say multiply by, and this is a kind of silly word, the foo. The foo. All right, and our foo is really just a fancy form of 1, and that's the FFOO. Foo, fancy form of 1. We want to get rid of this square root. So if I want to get rid of this square root, we've already noticed a little bit in multiplication that if I multiply the same thing times itself, it becomes a perfect square, and then we can get rid of the square root. So if I want to multiply the bottom by square root of 5, I have to do the same thing on the top. And really, square root of 5 over square root of 5, this whole thing is just equal to 1. So we're multiplying by a fancy form of 1 so that we can get rid of our radicals on the bottom. If we pick the right fancy form, then these radicals are going to go away. And now we multiply just like we did. So step 3 is to follow your multiplication rules, which were your last objectives. So hopefully we go back and we remember that. Our multiplication rules say that we multiply the outside with the outside and the inside with the inside. So here if I multiply the outside, I'm going to get 2 times 1 is just 2, and the inside is the square root of 5, over the outside is just 1 times 1, the inside is the square root of 25, and here we get this perfect root, which is exactly why we multiply this times itself. We want to choose the fancy form of 1 that's going to multiply to give us a perfect square, and now I can simplify my perfect square so that I just have 2 radical 5 over the square root of 25 simplifies to just 5. I want to check step 4. Check if radicals simplify. And no, they don't. The square root of 5 is as simple as I can get it. And then the last step is to check if coefficients can simplify. Meaning, can I simplify 2 over 5? And no, I can't. So this is going to be my final answer. So make sure you have all these key points down. And let's try number 3. So number 3, we see square root of 4 and square root of 3. The very first step we have is simplify any perfect roots. Do I have perfect roots? Yes, the square root of 4 is a perfect root. So actually, this problem becomes 2 over the square root of 3. The next step is to multiply by the foo, our fancy form of 1. I want to use the denominator, and I want to make sure I multiply it by its exact self so that it's going to turn into a perfect square and go away. And if I do the same thing on the bottom, I have to do it on the top. Then step 3, practice my multiplication rule. So I keep 2 on the outside, 3 on the inside. And the square root of 3 times 3 on the inside is the square root of 9. It does turn out to be perfect, so we picked the right foo. So I get 2 radical 3, and then 9 is the square root of 3. I want to check to see if my radicals can simplify. No, they can't. Check if my coefficients can simplify. 2 and 3 cannot. So again, I am done. So those are some examples when we have one term or a monomial over a monomial. But we can see things like 4 and 5 where we have a binomial over a monomial. So here we're going to have the same process, but when we have our multiplication step, we're going to have a little extra work. So I want to get rid of this radical on the bottom. There's nothing that I can simplify. So I want to multiply by my foo, square root of 17 times the square root of 17. Now, this is going to be like a distribution problem. My 17 needs to go to the first term and to the second term, and we still need to be following those multiplication rules. So negative 5 is the outside, 17 stays inside. I want to add. There's nothing outside, so really it's just going to be negative 6 times 17. Now, you could multiply this or leave it apart to help you factor when we want to simplify, but I can see 17 is prime and 6 is 2 times 3. So there's really nothing that I'm going to be able to simplify in this root, but we'll get to that. Over square root of 17 is the square root of 17. Now, hopefully you've seen the pattern. 17 times 17 is going to give us a big square root. And it's just going to simplify anyway because we're trying to create a perfect root. So what we really want to see is that the square root of 17 times the square root of 17 is going to give us the square root of 289. But rather than doing that extra step, the square root of 289 is 17. Hopefully you're starting to see that when you multiply the same root times the same root, you just get that number without the root. So if you can take that shortcut, great. If you want to expand it and then simplify it again, you can do that as well. So now the last thing we need to do is simplify under our root. So we have negative 5, the square root of 17, plus 6 times 17 is 102 over 17. We check if we can simplify our radicals. Again, 102, even though it seems like a big number that we would be able to pull some pairs out, we can't. And this is as simple as possible. So we might get some ugly answers, and that's okay. Now, let's look at number 5. Here again, we have a binomial, 2 terms over a monomial. I want to get rid of this radical, so I'm going to multiply it by my foo, square root of 18, and the square root of 18. Again, this is going to be a distribution type problem where it has to go to the 3 and to the radical 2. So let's go ahead and start simplifying this. 3 stays on the outside, radical 18 stays inside, plus nothing on the outside, but on the inside it's 2 times 18, and square root of 18 times square root of 18 is just going to give us our 18. We need to, after we multiply, check if we can simplify any of our radicals, and here we can simplify radicals. 18, I know, breaks up into 9 and 2, and 3 and 3. So I have 3 root 3, 3, and 2, plus, here I can break 18 up again. 3 and 6, and 2 and 3. So I have the 2 that was originally there, that we got from the first term. Then my 18 breaks up into 3, 2, and 3. And all of this is over 18. And so now we need to simplify. I can pull a pair of 3's out. I can pull a pair of 2's out and a pair of 3's out. So I get 3 times 3. And my 2 stays inside, plus I get a 2 that comes out, I get a 3 that comes out, and there's nothing left inside over 18. And now I just simplify. 3 times 3 is 9 radical 2, 2 times 3 is 6, all over 18. So simplifying our radicals definitely adds a little bit of work. And now the very last step is that we have to check, can we take out any numbers, or can we take out a number from all 3 terms? So maybe you're saying, oh, I know I can simplify 9 and 18. Only if you can simplify 9, 18, and 6 and 18 can you simplify. And I try and think of a common factor. I have 3 times 3, 3 times 2, and 3 times 6, so it does work. So I want to divide by 3, divide by 3, and divide by 3. So 9 divided by 3 gives me 3 radical 2. 6 divided by 3 gives me 2. And 18 divided by 3 gives me 6. And now there are no more numbers that I can take out of a 3 and a 6, and a 2 and a 6. So I have to stop, and that is my final answer. This is the problem that is most commonly forgotten. Alright, so quick tip, right, don't forget to simplify at the end. Alright, a lot of times we leave this answer, and that would be incorrect. We need to simplify all the way. So double check all the time when you get to your final answer, are there any common factors that we can take out? And one last example, and this one's a little tricky. This is not an I. This one's a little tricky because we have coefficients now in front of our radicals. So it's very similar to the last 2 examples, except for now we have a little bit more work to do. So here, same thing. Can I simplify any perfect roots? No. Can I simplify any of my, square roots? No. So I need to get rid of my radical in the denominator by multiplying by my foo, 4 the square root of 6, 4 the square root of 6. So this 4 stays with the 6. Even though it's just a radical that's the problem, the 4 is part of the problem, and we need to include that as well. So this is going to create a little bit more work for us. So again, we're going to distribute across, and our denominator is going to have a little bit more work as well. So I'm going to write this one out separately. Maybe you want to do your numerator work, and then your denominator work, and then you can put it back together at the end. So my numerator, I'm going to have 4 the square root of 6 times 2 plus 3 the square root of 2. So I'm going to follow my multiplication rules. 4 times 2, they're both outside, is 8. Square root of 6 stays inside. 4 times 3 is outside. 6 and 2 stay inside, which is 12. My denominator is going to be 4 radical 6 times 4 radical 6. Well, 4 times 4 is 16. The square root of 6 times the square root of 6 is the square root of 36, which we know is just 6. So this becomes 16 times 6, and we get 96. So now I can kind of push it back together and start to simplify. Maybe you want to simplify your radicals first. So I have 6 over here. I know that I can't break that up, but 12 is going to become 4 and 3, and 2 and 2, so that I can pull out in front. So this is going to be 8 radical 6, and 12 times 2 is 24 radical 3. Here's my numerator, all over 96. I can't simplify any more roots, I already did that, but I do need to check, can I simplify any of my coefficients? And yes, I can. And maybe you say, okay, well I know that I can take a 2, a 2, and a 2. Okay, well that gives me 4 radical 6 plus 12 radical 3, and 96 divided by 2 gives me 48. Right? So maybe you could simplify, but you need to check. Can I take out more? Yeah, and I hopefully see that I can take out 2's again, or even the bigger common factor, which is 4. I could take out a 4, I could take out a 4, and I could take out a 4. 4 divided by 4 just gives me 1 radical 6. 12 divided by 4 gives me 3 radical 3. And 48 divided by 4 gives me 12, and that is going to be my final answer. So over here, originally we could have taken an 8 out as well, and we would have just gone straight to this answer. But maybe you don't recognize that 8 is a common term. You could take out 2 and 2 and 2 and keep going until you finally get to this answer. It's just going to be a little bit more work with a few more steps, but you will get there eventually, even if you don't take out the greatest factor. So here we have a few to try on your own. Go ahead, pause the video, try it out, and then we'll come back and check to see if you're doing your work correctly. Okay, so these are the answers you should have gotten for 7 and 8. One thing I would like to point out, if you did make a mistake, or maybe you thought, man, these numbers are really big, this was a perfect root. So you could have simplified your 25 and gotten rid of all your radicals on the top, and then rationalize. If you rationalize and kept the square root of 25, it would work out, but your answers would be much bigger and you'd have a lot more simplification. So go back and check to make sure that you're not making any errors there. And here we have a few problems for your self-check. Make sure you're doing these problems in your notes so that we can come back tomorrow and talk to them during the do now.